afternoon, everyone. Maybe we can get us started. Yeah, thank you all for attending this talk. And today it's our great honor to have Professor Ninghui Li from Purdue University to give the talk. So Ninghui is currently a seminar Conte professor and associate department chair at computer science in Purdue University. Okay. And before that, he received his Ph.D. from New York University and was a research associate at Stanford University. Okay. His research involves security and privacy. Okay, so he is indeed a big name in our community. Okay, and he has received multiple Best Paper Awards and Test of Time Awards from security and database venues. Okay, he is currently serving as the chair of steering committee of ACM and CCS, and before that, he also served as the chair for multiple leading conferences like CCS, AsiaCCS, and so on. And Ninghui is also an ACM Fellow and IEEE Fellow. So please join me to welcome Ninghui for the talk.
Thank you. Yeah. Thank you, Julian, for the nice introduction, and thank you for inviting me. So I think I visited the Penn State a couple of times, I think most recently in 21, and I enjoyed every visit. So yeah, thank you for inviting me back here again. So yeah, today I want to talk about membership inference attacks. So I'll do a little bit the historical perspective and also talk about some of our recent research results from my group. So basically this talk is about membership inference attack against the machine learning models. So this cover one aspect of the security and privacy problem regarding machine learning models. So here I just want to delineate what's in scope. So there are other concerns about ML model. For example, there may be concern about the privacy of the model. You may be afraid that the attacker, by accessing the model, can steal it. So that's not what membership inference is about. So membership inference is about privacy of the training data. And even in this context, there are different attacks you may consider. So member inference attack is you assume the attacker have access to the target model, and he also have one target instance, and he tries to determine whether that instance is used in training the target model. And there are other attacks. Yeah, so there are also like attribute inference attack. You assume the attacker knows part of one instance, and then he's trying to infer the part that he doesn't know. So there's a paper on that. There's also this what I call representative instance instruction, which basically given access to the model, for example, face classifier, and then you can reconstruct a typical instance of one class. So for example, given access to the model, then you can say this person will look roughly like that. So personally, I'm not even sure, I wouldn't view that as a privacy concern, but this is also a research problem. So this paper focused on membership inference attack. So then, so this is outline. The first thing I want to talk about is why do we care about membership inference attack? To my knowledge, the first, I guess, the membership inference is reported in this paper in 2008. So this is a membership inference when publishing statistical information. So this is not an ML model, but you can view publishing statistical information is very similar to publishing ML model. And this is in the context of this genome-wide association studies. So this kind of study aimed at finding what genomic marker are related with the disease. So the way you do this research is you have a group of patients, and then you have a control group who don't have the disease, and then you get their genome information, and you measure the frequency on different locations on the genome, so known as these SNPs. So basically, these are the positions that within human population, there's differences. Usually, there are two different variants. Some people have A, some people have B. And if in the disease group, you have much higher people having, for example, A than B compared to the control group, then this is a genomic marker that is likely related with the genomic disease. So there are a ton of paper on this topic. And when they publish this kind of paper, they also publish an aggregated statistic of the SNP frequencies on each position, so at least in a publicly available form. So what this paper shows is that given that published aggregated statistics, and if you also know one individual's genome information, so therefore you know on each of the SNP whether this individual have variant A or B, and you also know the background SNP frequency in the background population. So when this individual is found within the population, what percentage having A versus B. So if you know these three pieces of information, you can infer whether this individual is a part of the disease group with very high confidence. And so before talking about how they did it, I want to talk about the consequence. Because privacy is not really purely technical concept. You can't just write down a math equation and say this is what privacy means. Because how do we know that math equation is right? So privacy is primarily a social, legal, moral context. So then the way for us to know that the privacy violation occurred is society agree. In this case, privacy violation occurred. We need to do something about it. So there are a number of such instances that happened over the last several decades. And this is one of them. So the consequence of this paper is that the US NIH and the UK similar organization, they changed the policy so that research paper will no longer publish this aggregated statistics because this is viewed as violating privacy. Because if you know one individual genome, you know the individual belongs to the disease group, you know the individual have the disease. But so the point is this is accepted as a privacy violation, and this is essentially membership inference. But actually, I talked with a colleague. They said after several years, they changed the policy back because this is viewed as hindering the research in this area. So, but anyway, the point is that this is considered as a privacy violation. So membership inference is considered a privacy violation. So this is a brief summary of how they did it. We have the published frequencies on each of the locations. So we just need to know information from the disease group. So what percentage have variant A on each of the locations? So we have this data from data published associated with the paper. And then we have the target individual. So on each of the location, whether it has A or not. So that column of yes, no corresponding to that. We also have the background population. In the background population, what percentage have A? So then if we look at every single location, we have a very weak signal, so which is whether the individual's information is consistent with the hypothesis that the individual is a member. So the first row is yes, because the target individual is having variant A, and in the disease group is the average of usually hundreds of individuals. So if the target individual belongs to the disease group, we would expect this number here to be slightly higher than that because this individual will contribute 1 to this. On the other hand, if the target individual is 0, we would expect this disease group is slightly lower than the population average. So then on every SNP location, we get a signal whether the target being a member is consistent with what we are observing. So if you look at every single SNP, this signal is very noisy because this is averaging of 100. However, when you have tens of thousands of such noisy signals and aggregating them, you get a very high confidence inference. So that's basically what this paper does. So the point I want to make is that in this case, membership disclosure means that people agree there's a privacy leakage in this context. And then on the other hand, what we want to know is, can we have privacy leakage without membership disclosure? And what I'm trying to say is that in a sense, no. So in a sense, membership inference equals privacy disclosure. So therefore, we want to study membership inference. So this is I'm going to give a kind of little bit of long detour to try to convince you that membership, if you want to have a privacy violation, there has to be membership leakage. So to do that, we first we want to define what is the privacy. And this is one early attempt at defining what is the privacy, and it's a very natural idea. So this is in the context of a statistical database. So basically, when U.S. Census Bureau and other organizations publish statistical information, they want to know whether publishing the statistical information lead to privacy violation. So then one attempt at defining there is a privacy leakage is to say, if access this statistical information, when access this, we should not enable adversary to learn anything new about the individual. So about a single individual, before I access the database, I know something. But after I access the database, I should not learn anything new, or at least it should be bounded about the individual. I may learn information about groups. I may learn information about the larger population, but I shouldn't learn information specific to one individual. So this is a very natural definition. And in fact, there's quite similar to the notion of a semantic security for encryption, which is the standard for encryption. However, it turns out that this is not possible if one wants utility. And so this fact was discovered by the inventor of differential privacy. Differential privacy basically motivated by this natural definition actually is unachievable. And this gives an example of why it is unachievable. So assuming that we do not yet know smoking causes cancer, and then some organization did a study, study a large amount of individuals, and then these study results demonstrate the connection, and then they want to publish this result. Now, suppose we have someone who is a smoker, and let's say the smoker, his smoking is the public knowledge. Maybe he posts his, pictures on Instagram, Facebook, whatever. Now, the question is, can this smoker Carl complain that you shouldn't publish your result? If you publish, you violate my privacy. If you look at the definition on the previous slide, that is true. Indeed, publishing this result enables people to learn that Carl has a higher chance of getting cancer. Before you publish the result, nobody knows smoking causes cancer. Everyone only knows Carl smoked, but doesn't know Carl has a higher chance of getting cancer. By publishing the result, you enable people to make that inference. Carl has a higher chance of getting cancer. So indeed, the publishing result enable people to learn something new about this individual, and you can argue this is actually quite sensitive information. There's a consequence. So if we follow that definition, we would not allow publishing of this result. So obviously that's ludicrous, right? So in fact, this can happen even if Carl was not even involved in the study. So the study using other people's data, but establish a correlation. So unless we are willing basically to say nobody do any study for statistical correlation and public result, we have to say this is not a privacy violation in this context. So then differential privacy is basically defining in a way so that can differentiate that this is not a privacy violation, but other cases are. So this is I guess the original pure differential privacy definition, epsilon differential privacy definition. So if you haven't seen this before, this may look very daunting. So in fact, even if you, I remember when the differential privacy paper, maybe I first saw it, I don't know, in around 2008-ish, but I didn't get it until like a couple years later. So it's not, I guess, intuitively, I guess, very easy to understand. But the way I tend to understand it now is like for any individual whose data is in the data set D, and then we want to apply algorithm A and then publish a result, what we want is we define an ideal world of privacy for that individual. And that is easy to define. That is, I will take that individual's data outside the D and then get the data set D prime. So this is the definition here is the neighboring data D and D prime. Basically, D and D prime will differ in one individual's information. So after I get D prime, if what I'm publishing on D is essentially similar to what I'm publishing on D prime, then you shouldn't complain that your privacy is violated. Because whatever you are complaining, I could have published exactly the same thing if I remove your data and just publish, do the study, use everyone else's data and publish this information. From D prime, I publish the information. So then this deal with the Carl smoking situation, because whatever inference you can make from Carl, it can happen even if you don't use Carl's data in this study. So this is I think differential privacy is a very elegant mathematical definition. It gets around this complexity of defining privacy by thinking about what is the ideal world for every individual, which is you take out that individual data, then that individual doesn't get to complain about privacy violation, even though new information can be learned about that individual. So then this is, so I think most people know that there's the very consequential, the privacy definition and widely accepted today. So then the point is that differential privacy is related with membership inference. So, and this is work done by my group, so in 2013. So at that point, I was trying to see whether we can weaken differential privacy, whether differential privacy is maybe too strong. So then we want to get to the bottom of what privacy means. And then what we came up with this membership privacy framework. So the adversary is assumed to have some prior belief about the initial data set. So then this prior belief about the data set will give the adversary prior probability of any individual item's membership. So before I observe anything, I know I have some prior belief about what is the training data you can think of. And then this training data will give me a prior belief about any individuals, whether the individual's data is in the training or not, so the membership. And then after I observe the output of the algorithm, and then I can update my belief using Bayes' rule and using knowledge of the algorithm. So then I obtain a posterior probability of T's membership. So then what membership privacy requires is that for any tuple T, for any data item, so any individual's data, the difference between the posterior belief of membership and the prior membership should not be too different. So it should be bounded by some parameter. And so then this membership privacy is no longer a single definition. It's parameterized by what is the family of a prior distribution we allow the adversary to have. And it turns out that this impossibility of privacy as a secrecy defined as this car smoker example is captured here by the fact that if we require membership privacy for the family of all possible distribution, that basically is infeasible. Because the adversary, the prior belief may be one data set and another totally different data set. For example, maybe the adversary know the data either about all boys or about all girls. And then by membership inference, then if I want to satisfy membership privacy, so limiting the membership gain, then we require on these two totally different data sets, we have to publish something that are similar. Because otherwise I can tell which one is it, whether it's all boys data set or all girl data. Therefore, I know membership. Because if it's a boy, then I know if the boy data set is used, then the boy is member. I will get a significant increase in the membership inference. So basically, if I don't limit what is the prior allowed prior distribution, then satisfying this basically require no utility. So for every possible different data set, you have to publish something that are similar. Otherwise, I can infer membership. So then basically, you have to make some assumption about the adversary prior belief. And maybe what's most interesting in this work is we find that differential privacy is equivalent to membership privacy under the family where the distribution have the property that membership of different individuals are mutually independent. So whether one person's data is included in training is totally independent of whether another person's data is included in the training. If we only allow the adversary to have these kind of beliefs as a prior distribution, then satisfying membership inference is equivalent to differential privacy. So then, in some sense, this is actually there were. At least in the earlier years, there was some discussion about whether differential privacy is strong enough or it's still weak. It's essentially boiled down to this problem. So differential privacy makes sense when you assume membership are all independent. When membership are not independent, for example, if we define differential privacy relative to a single individual, but in fact that for example, in medical domain, either the whole family's data is in the data set or not, then satisfied differential privacy may not be good enough because membership are not totally independent. So whether it's good enough will depend on whether the assumption of membership are totally independent makes sense. So in fact, I've seen many papers where differential privacy is applied in a setting where I personally think are not appropriate. And essentially it boils down to when I define a neighboring data set, whether the difference is really something, a unit that's mutually independent with other things member, and whether that capture the whole contribution of one individual. So yeah, so this is just within the framework, we consider the multiple kind of instantiation of membership privacy, where we restrict the diversity with prior belief to be some possible distribution. So essentially, if we don't place any restriction, we get this, you want to satisfy this privacy, you have to totally give up utility. And there are two different variants of differential privacy. So unbounded differential privacy refer to, when I'm defining differential privacy, the two neighboring data set D and D prime will have differ in one record in the sense that you totally remove one record from one data set D, and then you get D prime. So one of them have one more record than the other. Bounded differential privacy is when I'm using differential privacy, I said they always have the same number of records. So the two neighboring data sets is I replace one record with some other value, and you get a bounded differential privacy. So they will correspond to membership privacy with slightly different distribution. So they are all, basically it's all assuming independent. Just one of them conditioned on the data set of the same size. And I remember actually proving that bounded differential privacy equivalent to this is the most technically challenging part, and I couldn't do it. I had a colleague who recently joined Purdue at that point in theory, so he was able to do the probability kind of math to make it work. And then there's some other kind of privacy notion proposed before this paper. So this one actually from my earlier paper, trying to relate differential privacy on the sample, trying to relate k-anonymization with differential privacy. So we came up with some weakened version of differential privacy. And then the differential identifiability is from another faculty member in our department, Chris Clifton's work. So we show that they are all basically subcases of this membership privacy. So then the point is that because of equivalence of membership inference and the differential privacy, you can view that membership inference as the empirical evaluation of differential privacy. So one way to use differential privacy, you prove your algorithm satisfy it. But sometimes the proofs are really hard. Sometimes what you can prove are not tight. So membership inference can be viewed as a empirical evaluation of a differential privacy parameter. If for every attack I try, I cannot break this up to some parameter, then this can be viewed as an empirical evidence that is satisfied DP for that parameter. So in fact, that the I guess actually active area of DP auditing is basically using this observation. And I want to say, because of equivalence, membership inference can be viewed as a universal test for privacy. So I remember first learning the concept universal test from the kind of sitting in Dan Bonet's advanced crypto class. He talked about pseudo-random number generator. So in the 70s, there were, when people define what is a good pseudo-random number generator, they list like a huge list of statistical tests. So I think this was from Don Knuth's book, there's 20-something different tests. You run this test on pseudo-random number generator. If they pass all of them, you say this is a good pseudo-random number generator. And so later, so Andrew Yao, so the Turing Award, Andrew Yao's one major contribution he has is he identified the next bit test as universal. So if looking at what's generated by pseudo-random generator up to some point, you're going to predict the next. If that test, if no algorithm can do that test, then this is pseudo-random. So he proved that this is universal. So this is only, you only need to do this one test. So of course you can't possibly enumerate the algorithm. So you still need to prove pseudo-random number generator by assuming hardness of some problem. But that's so here I feel that membership inference can be viewed as a universal test for privacy. But I do want to say that membership inference doesn't address all the data confidentiality concerns. So for example, if I'm training on my proprietary the whole proprietary company data model, then even though the diversity cannot determine membership of any individual record, they can learn aggregated information about your proprietary database. And that may be a concern. So that concern is not addressed by differential privacy and it's not addressed by membership inference. So it has its limitation. So in fact, that membership inference against machine learning and has been used in various places. It has been used as privacy auditing tools. For like DP auditing, or just and also be used to measure the effectiveness of machine learning. So that's also a domain has a lot of I think challenges, but at least empirically, a lot of time people use the membership inference to measure that. And I think more interestingly, for example, for LLM, it's be used to part of training data extraction. So for example, one way to try to extract training data from LLM is you ask it to generate. But after it generates the sequence, you want to know whether this is really used in training or this is just because it wants to generate it. And you can do that using membership inference attack. And also a very useful thing is against the LLM, pre-training membership inference is very hard because in pre-training, you will scan huge amount of data and sometimes scan the data only once. So inferring individual documents membership is very hard. But if you have a huge data set, for example, if New York Times want to prove that their data set is used in training some model, they can collect very weak membership signal of each individual article and then combine them to say you use my data set to train. And so there are some data set inference methodology are proposed in recent years, basically building on membership inference. And another interesting application is the test set contamination. Because all these models, they want to show they perform really well on this benchmark, and some of the benchmarks are basically public. So how do you know the new model perform well because it's really good or because it's basically trained on the benchmark? So then there's a paper on test set contamination, basically detecting whether this specific benchmark formulation is used in training. So, and then similarly, copyright detection. So yeah, so I hope I've given plenty of reason why membership inference is an important area. And that's only the first part. So, so I think some of the later topic I'll just skip very quickly. So I want to talk about how to define membership inference because in security, it's very important to get the definitions right. So to define that, we first need to consider adversary model. So first, there are different kind of access to the target model. So label owning, the attacker can only query the target model, get a prediction. So in this case, let's just consider classification. So for this case, so I get the classified label. But most of the time, we assume that we get the classified label, we also get the output logit. So get a little bit more than just a label. And in white boxes, we have the model. So then we have all the parameters, we can do whatever we want with it. And then there's also federated learning setting is we are doing the membership inference during training. So the server can be malicious. So he sees every gradient update. So then this is even more information than the final parameter. And then generally, we assume that the adversary have access to the same distribution as the training data because without it, it's really difficult to say they have different distribution. How do you measure them? But yeah, this is, and also, it's difficult to say that this thing can be kept secret. So that's a common assumption is adversary have access to the same distribution. And usually we assume the adversary also know the model architecture and the exact training recipe so that the adversary can train similar models by sampling data and then train similar models. And these are usually known as the shadow models. So for the different, so then what's important is we get some signal of members. So that if we see this number high, we know it's likely to be a member. So under different access, there are different signals have been proposed. So for label owning, one of them is just use prediction. So in fact, so a baseline membership inference attack is simply, if you predict correctly, I say this is a member. If you predict it wrong, I say this is non-member. So while this sounds like so rudimentary, if you use some metric like balance accuracy, this is actually pretty hard to beat. So in our first paper, we find that many proposed attacks can beat this one. And even though those one can beat this one on balance accuracy, they cannot beat it by too much. So, and the black box, usually we will use model loss. And it turns out that the loss is, so this scaled predict confidence is basically equivalent to the loss. But when presented this form, it's a little bit better signal because they tend to follow Gaussian distribution when you consider different cases. So basically, the predicted confidence of the correct label, so the divided by 1 minus p, and you take log. So that turns out to be the default signal used by most of the most effective membership inference attack against classifiers. And then in the case of white box, some earlier paper used the activation map of neurons, and then you train like a classifier, but they don't work very well. It seems using norm of the gradient from target instance works a little bit better. And I think it's still a little bit open that can we do significant better in white box case in terms of membership inference compared to black box. And so far, I haven't seen white box attacks that are really more effective than black box. I don't know whether that's inherent or that's actually just we haven't found the really good signal. Either case could be possible. I think that's an interesting problem. I don't know how to tackle that. So another thing is evaluation matrix. So membership inference attack will output a score, which is a scalar value. So then use that we can using standard metrics like AUC, like balance accuracy. But when we use this, a lot of the attacks will be very similar. So it's very difficult to get very high on this. So in Nicholas Collini in 2022, in the paper proposed that we should really focus on the high confidence instances. So basically, if the attacker try to determine membership with very, very low false positive, then how much the attacker, so the true positive rate at very low false positive rate should be used as the right metric, because the attacker only makes the most confident inference. So this makes sense because privacy, you have to protect the worst case. You cannot say on average everyone's privacy is protected, but some individuals' privacy are leaked. So that's not acceptable. So in some other talk, I give more examples to illustrate that, but I think that's, so therefore this is a reasonable, so this is a reasonable metric to focus on compared to balance accuracy. So at high level, why inferring membership is hard? So I believe this is because whatever signal you are looking at for one instance, it will impact it not just by that instance, but also by other instance. So for example, if I have two instances if many instances are similar to one target instance, XY, then even if XY is not a member, when the training data set includes a lot of instances similar to XY, the loss will be really low. So when seeing that the loss is really low on an instance, it could be due to XY is directly included in training, or it could be that XY is just easy instance. So lots of other things are similar. So by training on any sample, you will have a very low loss on the instance. Or it could be that there are some instances that are kind of contradictory to XY. So maybe the features are very similar, but the label are different. So then even if you include this XY in training, so maybe it's just a kind of borderline hard instance, even if you include in training, the loss will not be very low. So you cannot differentiate this by just looking at the signal by itself. So we need to somehow make the MIA understand this kind of relationship. And the way to do it is to train shadow models. So again, Nicholas Collini's paper. So this he proposed this likelihood ratio attack called LIRA. So this is the basic idea. So the way we learn this kind of relation is by training lots of shadow models. So for example, for every instance, we will, so first this is the kind of the idea of the attack. The actual attack doesn't work like this because this means that for every instance, we need to do huge amount of training. But just to show the idea first. So for every instance, we sample a subset from the data distribution, so the attacker do that. And then he trained two models. One of them is the sample adding at this instance, target instance. The other is excluded. So I get an in model and an out model. So then after repeating this n time, I get n in model and n out model. So then given this, then I can query XY on all the in model and out model, and looking at my signal, I get a distribution. So then the membership is basically determined by, I'm trying to tell which distribution the target model I'm trying to attack will also give me one number, give me a line. So where does that line, which distribution does that line fall? So then this is basically a likelihood ratio attack. So for every instance, we have the distribution of the signal. So you can think of this basically marrying the loss. So you can think of this loss, some function of the loss. So on all the in models, all the in shadow models I train, I get loss like this. And all the out model, I get loss like this. Now, if I get, let's say, something here, then I'm going to say, oh, it's probably in. If I get something here, I'm going to say it's probably out. And then the standard statistical test for this is I can do a likelihood ratio test, which I think is theoretically the strongest test you can do. And this using this log function will tend to make this follow Gaussian. So basically, you learn the Gaussian parameters and then you do likelihood ratio test. So this is known as the Lira attack. So is this practical? So this actually performed very well. So while there are actually until very recently, basically no algorithm really beat Lira. You may see that in some papers they claim differently, but I think a lot of them is due to confusion. They are beating another attack in the same paper that are really shouldn't be called Lira, but it's called Lira. So anyway, so this slide is on that. So it is the practical. So the algorithm description is definitely not, because for every target instance, we will train 2n shadow models. So that's really not how people do. So even the Lira paper have algorithm presented that way, but their code will not be doing that because that's just infeasible. So what people are actually doing is, so given a data set D, so we can generate, let's say, 2n plus 1 subsample data set where every instance is sampled at probability half. And then we will train 2n plus 1 models, each one using one of the subsample data. And then we pick one of these 2n plus as the target models. And then we treat the remaining 2n as a shadow model the attacker can use to attack. And then for each instance, it's expected to be member of about n shadow models. So expected we have, for every instance, we have n in models and n out models. For different instances, the collection of in and out model will be different. But for every instance, I have a collection of in model carry out, then I can carry out a Lira attack. I can get this two Gaussian distribution, and then I do likelihood ratio. Now the question is, this is not really practical, right? If you think about in real world, you're trying to do an attack, it's like, oh, now I want to determine membership of this instance. And then maybe tomorrow I want to determine membership of another instance. Basically, you get the membership queries like kind of in a streaming fashion, and you don't want to pay huge amount of cost for every single query. So therefore, you will train all your shadow model first before you get any queries. But what this means is that I don't have in models for the query instance, because I will get query of instance that I didn't know exist before. So then I need to determine whether that thing is a member or not. So then in the Lira paper, this is handled by, in this case, we only have shadow out models. So rather than this two Gaussian distribution, trying to tell which one you fall into, we only have this, and then I'm just trying to tell whether the observation of a target model fits this distribution or not. If it fits, I say, oh, it's probably non-member. If it doesn't fit, I say it's probably a member. So the problem is that become a lot less accurate because I don't know this, I don't have this in distribution. So this algorithm is known as Lira offline, I think from the original paper. But I think it's really a bad name because there's no ratio, there's no likelihood. It's just fitting on a single Gaussian distribution. So after the Lira paper, in fact, even before the Lira paper, shadow training is widely used for membership inference. In fact, all the recent MIAs are based on shadow models. And then their study extending the idea to other models. And this Lira in this online setting is really hard to beat. And this so in fact, this is remain one of the strongest attacks. And I do think that we are able to improve on Lira in our written papers, but yeah, for later. But in non-adaptive setting, this performed very poorly. So recently, most of the paper focus on the non-adaptive setting, in part because it's more realistic, in part because the online setting is so hard to improve upon. So now let's talk about how do we define a membership inference in a formal game, security game. So the key issues, I believe, is the relationship between these three data sets. So there's this data set for the training the target model. We call that data set D. And then there's a set of query the adversary need to answer. We call that D query. And then there's the set of auxiliary data set the adversary have, which can be viewed as drawn from the underlying data distribution. We call that DADV. So for most of the MIA papers, the query set will include basically all the members, and then typically another half, which are non-members. And then the adversary, the algorithm, the MIA algorithm is supposed to determine membership of this within the D query. The key thing is what's the relation between D query and DADV? So in the adaptive setting, which is basically the online setting, where basically the D query will be part of DADV. So when the attacker tries to train shadow models, he already knows what are the queries. So then he can train in models. Before our paper, there's a membership inference was formalized as a game, but it's done in a way that's, I believe, a little bit problematic because it doesn't really allow you to differentiate these two settings. So typically, it's defined as a membership inference a single instance. So there's the challenger will sample a data set, and then train a model, and then randomly decide whether to choose a member or choose a non-member. And then the challenger will give this a single query instance together with access to a target model to the adversary. Then the adversary will try to guess whether this is a member or not. Because it's defined as a single instance, you can't really differentiate whether it's an adaptive setting or non-adaptive setting. So we try to define the membership inference in a way that allows us to differentiate this. So essentially, the challenger will sample a data set D and then train a model. And then the challenger will sample a query set. So then part of it is the members. So the DA part are members taken from the training data set. And the DB part are non-members. So here we assume that when you make independent sample data set from the same distribution, the probability of they are sampling the same instance is very low, so the overlap is very small. So yeah, I guess so that's why we didn't bother to say you remove all the things in D from DB. But basically, DA are supposed to be members, DB are supposed to be non-members. And then the adversary will get this co-query data set, and then the adversary need to guess which among these are members. So the adversary will return with a set of guesses of members. So the benefit of doing this is we can now differentiate adaptive setting and non-adaptive setting by constraining when the adversary is allowed to train shadow models. So adaptive setting, the adversary can train shadow model after receiving this query set. So then the adversary can train basically use this query set as his own auxiliary data set for training shadow model. Then he have both in and out shadow model. He can use Lyra. Non-adaptive setting require the adversary to do all the shadow model training before the adversary sees this data set. So then he will not have in model. He only have out models. So that's the difference. So then, I guess, yeah. So recently we have two papers on new attacks for membership inference. So one of them is this cascading membership inference attack. It's basically trying to exploit the observation that membership of different instances are dependent. So if X and Y, if two X1 and X2 are very similar instances, if I determine X1 is a member, then the fact that X2 has a low loss is already kind of explained by the membership of X1. So therefore, we should be less confident. So therefore, the idea is that we gradually determine membership. So yeah, so I guess this is just a kind of a little bit the standard the probability graph model. When you have two things both impact outcome, so and we're trying to from outcome to infer this membership of different individuals. So the membership are not independent. So even though a priori their membership independent, conditioned on what I'm observing, they become dependent on each other. So then what our attack is actually I think it's a very simple idea is let's first perform a membership inference attack and then identify the ones that I'm very, very confident on. I'm pretty sure are correct. Then I will determine that for this target model, I know these are members, these are non-members. Now I'm going to train new shadow model by fixing those. So fixing member number. Then I train some new shadow model. Then I use this to do membership inference attack. And then I make some additional very high confidence inference, and then I iterate. So the idea is basically adapting the shadow model to the very confident inference that I have made. So this can be applied you can instantiate the base attack using any of the existing membership inference attack. So this is more like a framework. You just iterate, and then when you train shadow models, when you train shadow models, you take advantage of a high confidence inference you already made. Yeah, so that's the high level idea. This is basically saying the same thing. So just, I guess on the, so we're able to, so this is applying our cascading membership inference framework using Lyra as a baseline. So then I guess on the hardest data set, for example, MNIST, on like a very low, like 0.001% FPR, we're able to improve the true positive rate from 0.12 to 0.77. So this basically means that when I'm making a guess at this confidence level, I have a 770 to 1, like odds that this is my guess is correct. So this is very hard. I'm able to guess the most vulnerable one I can guess very, very high confidence. So yeah, so we can improve like on this true positive rate at a low confidence for all of the attacks. You use this to instantiate this cascading framework, you can get better results. So in some cases the improvement is less, but the improvement the highest on the kind of the hardest case. Yeah, so then we also show that the most benefit you get are from the first couple of iterations. So making guess and then training shadow models using those guess. So beyond a couple of iterations is really not helping too much. So then, well, this is better in terms of some of the metrics. First, it's only applicable for the adaptive setting. So we have both in and out model. And second, this is take a lot of computation. So we need to train essentially however number of iteration steps we need to train. For each iteration step, we need to pay the same cost of as Lyra. So I think the only reason that we're able to run the training was because we are collaborating with a faculty member who was at NVIDIA labs. So my students are basically using NVIDIA's GPUs to do the training. So now the question is, can we take advantage of this observation that membership are really dependent on each other, but do something more efficient? So then we have this what we call imitative MIA. So the intuition is that, so first to, I guess, recap, the challenge is the membership of different instances are dependent. So cascading MIA exploit this, but it's really expensive. So then we observe that essentially the shadow training is independent from model we are targeting. So we're trying to learn how the model will behave depending on whether they include certain instance or not include. But all these in and out model, except the cascading one, kind of trying to take advantage of the target model in the way of learning anchor instances. But all the other attacks just learn generic behavior. So the shadow models are totally independent from target model. So then it should be possible to take advantage of accessing the shadow model, take advantage of the target model, so that we train more targeted shadow model. So this is our idea. It's essentially, you can view this, so this is a high level idea, is given the target model, F theta is the target model, we basically, you can view this imitate as basically the distillation, model distillation. So I sample data set DA, and then I run model distillation on the target model. Then I get a new model FA. So then the intuition is anything that's not included in this data set DA, I can view it as a non-member for this model, new model FA. And this FA is specific to the target model because it is sort of distilled from the target model. And then to get membership behavior, I will further fine-tune that FA on another data set to get a new model. So then for any data set, any instance in DB, I can view FB as the in model because FB is sort of trained on that model. So this way, for every instance, I can get a set of models that are sort of out this instance not direct using training and the static model that's in, and then we can apply LIRA. So here the detail doesn't really matter. We are essentially doing something very similar to LIRA, and also this imitate. We find that you can get slightly better compared to distillation by using a somewhat different loss function. But yeah, so basically the higher level idea of this is LIRA will just learn this, but these are independent from target model. So then we use imitation. We can learn two distributions that are a lot more targeted to the target model, a lot more specific to the target model. So this explains the loss function we use for the imitative training. It's not terribly important. In fact, it's possible to, if you just use model distillation, it gets a little bit worse result. But yeah, but it's essentially trying to preserve the signals that are really useful in membership inference in this kind of model distillation setting. So then one major advantage of this, we can also apply this in non-adaptive setting. So even when I don't know the target instance, so I can choose some what we call pivot instances. So these are instances that have very low loss on the target model. So then we view this as the likely members, and then we will fine tune on this pivot model to get the in models. So then for membership inference, so we have all the out models, and then to get the in model behavior, we will find instances that are similar to the current target instance, and then I will find among the pivot instances that things are similar. Then I will use those ones' behavior to build the in model. So I think in this approach, there's a good intuition behind it, but the precise math is a little bit sketchy. So if you want to get on because we are saying these are out models, but we are actually distilling the model that might be trained on the instance. But because of this distillation step, and we are using other instance, the impact of any single instance should be very small. So we can kind of view them as out models. So this kind of illustrates why this works. So the top row are what we get from shadow model. The bottom are what we get from the imitative model. And then there are 6 different instances. So this is the signal we get from this. And you can see the strength of this imitative is we get very concentrated distribution. So then telling this belong to here is, so first, these first two are easy, member and non-member. You don't need this. But when we get to here, you can see that for this particular instance, the in behavior and out behavior over all the data set are really overlapped. So these are the cases where I think LIRA would make a mistake. But by training this imitative model, both in and out are like a narrower, and then the out shifted bit. So then you can see, oh, this should be a member, and then that one should be a non-member. So basically, this imitative model allows us to narrow the in and out model behavior by specifically tailored to the target model, and therefore get more narrow distribution, and therefore get better result. So yeah, so I'm going to skip the numbers. Yeah, so in terms of open problems, I guess some question that personally I'm very interested in is, do white box access to target model provide more effective membership signals? So in fact, recently my student who worked on the 2 previous papers, Yuntao Du, is working on this, and he's able to find the membership signals that behave very similarly to the backmark, but we cannot get better. So I don't know whether that's inherent or it's just that we haven't found the right one. And also I'm curious, in the label-only model access, what are the most effective membership inference signals? So yeah, I'm happy to stop here and take any questions.
Thank you. This is a great presentation on the landscape of this problem. I have 2 questions.
Yeah.
First, you mentioned about the New York Times legal case.
Yes.
So from your perspective, in theory, New York Times has all the resources, and if they can create all the shadow models, for instance, right? So in theory, I guess, technically it's possible for them to prove that the articles were used.
Right.
Can you comment a little bit?
Yeah, so first, I believe actually we are kind of, I'm using that example and other people are using example in a little bit kind of bait and switch. Because I think the key issue in the real legal case is not whether OpenAI used the New York Times article data to train, but whether the use is fair use or not. Because I don't think OpenAI is denying that they are training use the New York Times article. The question is whether this use, because fair use is a complicated legal concept, right? So for example, I think when library first started, it was a legal issue. Whether you can buy a book and then just lend it to others, wouldn't that hurt the publishers and the authors' income? So it is, right? But the legal framework decided that is a fair use. So having public library buy the book once and lend to many people, that's possible. The question is, given a generative model trained on this and then generated text and make money from it, is that fair use or not? I believe that is a key legal issue. And in the technical issue of whether New York Times can prove, I don't think it's actually so easy, right? So because, so in fact, there are several research articles demonstrating how to prove this LLM is trained using a data set. So at least some of them are flawed. So for example, one approach is assuming that New York Times will have another set of articles which are similar distribution but have not been published. For example, earlier draft of the articles. So then if New York Times produce this other data set, and then they demonstrate that these should be the same distribution as the published article, but the model strongly prefer the published one compared to, then that should mean the model is trained on the, however, because New York Times is responsible in coming up with this set, then it's possible for them to manipulate this set, that even if it's not trained on the published article, I can manipulate so that the model will prefer the published one to this, because I already have the model. I can tune my data set specific for that purpose. So there's some other article, which very recent article, trying to generate, given the published data set, you generate another data set that should be the same distribution and then see whether the model prefer one to the other. But I haven't looked, I suspect it's also maybe breakable to some extent. So even that, I think, is still an interesting technical challenge.
Thank you. So second question is if the membership inference is not about the verbatim membership,
right,
but more like the paraphrase or the modified format, how does this finding usually work?
So they basically fail. So in fact, that one of my other papers, my student Kaiyuan Zhang, who's on the job market, by the way, I think he applied to Penn State, by the way. so yeah, he was looking at membership inference in the fine-tuning LLM phase. And then initially he tried to come up with better attack by assembling all this attack. So you get a little bit better, but not that much better. But then in the end, he came up with a defense, which at first I thought that, oh, this is so trivial. But what the defense does is before you use the text to fine-tune a model, you paraphrase it first. You do some selection about which one you use, but you select the ones that are vulnerable, you paraphrase them, and then you train the fun. And this basically defeats all the membership inference attack, because all the membership inference attack in the large language model is basically looking at token level loss. So once it's paraphrased, that signal is gone. So in this, people have not figured out what is this kind of meaning that, I guess membership is based on meaning rather than based on pure text, because I think it's just so hard to precisely define. Yeah, so I think the paraphrasing would defeat the membership attack. So right now, the membership inference are pretty much verbatim based.
Thank you, Professor, for this wonderful presentation. So, Professor, according to my understanding, the membership inference attack, the success rate depends on how well the adversary can infer the prior distributions of training dataset.
I guess maybe no. So I guess first we assume that the attacker has access to the same distribution. So attacker knows how the data set is sampled, but the attacker doesn't know what's the specific sampled result that resulted in this training. So what the attacker is really trying to learn is what is the model's behavior in general if I don't include this thing as the training data, and if I include this as the training data. So then at least Lyra is basically just that. They learn that's two distributions, and then they try to see which one fits.
Yes, Professor. And Professor, the attacker has made some assumption on the distribution, I think.
I don't think it. So the attacker just you assume you have the same access to the same distribution.
Yeah.
So and in practice, it's basically they're all sampled from the data set that you use for evaluation. But it's, the assumption is that the model trainer and the attacker are sampling from the same distribution, but the attacker doesn't know the specific sample result of the model trainer, and then try to infer that.
So, Professor, the attacker has access to the original dataset, training dataset.
So the data set is assumed to be sampled from a distribution. You can also view it as the training data set is subsampled from a larger data set. The attacker knows the larger data set.
Oh, okay. I got it.
But doesn't know, yeah.
Thank you, Professor.
Yeah.
Thank you, Professor, for the wonderful talk. I just have one question
Yeah.
on this slide here.
Yeah.
So it says the answer seems to be no to the question of do white box access to target model provides more
Right.
effective, right?
Yeah.
So does white box access also includes black box access? So given a black box access to a model, you could also do black box access attacks. So
Right.
do people try to aggregate signals from black box plus some signal from white box, and there's improvement?
So based on my knowledge, which is I guess largely based on my student interpretation about the answer is no, because so my student Yuntao was reasonably able to come up with, based on analyzing the different the gradient information, he come up with the attacks that are very similar result as the black box access. Then I told him, well, if you have multiple signals that get very similar result, can't you combine them to get better result? He hasn't been able to do that.
So no improvement.
It's counterintuitive. Yeah, I guess it should be able to. So I guess on the one hand, it is counterintuitive because you have model parameter, you have everything, you have so much more, you should be able to do better. But on the other hand, if you think about, well, what does the being member mean? Being a member means that the training is trying to lower its loss. That's the only thing this thing being a member matters. So therefore, maybe this loss is the only thing that indicates membership. So anything else is superficial. So that it is also theoretically possible that indeed the white box access is no better than black box access for membership inference. So I don't know whether that's possible to formalize and prove it, but it is a possibility. Yeah. I think it would be a great research topic. It's just that I don't know enough math to do it. Yeah.
Professor, I have one more question.
Yeah.
Consider cloud service models.
Yeah.
Cloud service model. So the attacker doesn't know the training data set in this case. So how can we launch the attack?
So then that's why all this. That's why this non-adaptive setting is more realistic. So in some sense, but at least what you do know is that you can sample data that are probably not in the training data set, but at least it will be similar. So assumed from same distribution. So that's the non-adaptive setting is the attacker can sample a data set that are from same distribution as the training data set, but are not really overlapping with it. So then you try to do membership inference attack. So then the standard Lyra-based attack is pretty bad because you only have out behavior. And then this our imitative attack is basically trying to do that by I distill something from the target model, and then this will help me dramatically. Oh, and I think maybe I skipped over another benefit of the imitative attack is much more efficient than the other attacks. So because we only need to train very few imitative model in order for this to work effectively. We don't need for the Lyra attack, we need enough data point to fit the Gaussian distribution. Here, I guess part of the reason we are using something like this a little bit ad hoc fitting model is we don't need basically we only need the mean for the two distributions. In and out, we're just estimating the mean. We assume everything have the same standard deviation. So because we don't need then we need very few, and it turns out that this already work very well. So basically, this is kind of one way to deal with the case in the cloud service setting.
Thank you, Professor. Thanks for it.
Was there another?
Thank you, Professor, for this wonderful talk. So I have a question. In the beginning slides, you have mentioned that in the federated setups, you can also do this MI attack.
Yeah.
So in a federated setup, what if instead of just inferring that whether the member is a participant in the dataset, the trending dataset or not, if can it be like, can we infer whether like what's the likelihood of having a member from a particular client, so that I can focus my target attack more targeted towards that client?
Yeah. So essentially in the federated setting, the attack is against each individual client. I'm trying to determine. So at least when we assume the server is a adversary, so the server is trying to tell this client whether this instance is a member of this client. So he do this attack against different clients separately. So in fact, another of my PhD student graduated a couple of years ago. We had a clear paper doing this on federated learning. Essentially, the idea is you know what gradient this one instance will generate, and then you observe this average instance from the batch. You are trying to tell whether this one is included in the averaging or not. So it's basically, yeah. So and then you can repeat this on a lot of these different epochs. So each time you receive, you can do this attack. So it is we get the result, I think, better than in the black box setting. But actually, personally, I felt that it should be do a lot more better. But it turns out that's not the case. So in some sense, it's kind of you're trying to determine whether you have a very high dimensional vectors, which are the gradient, and you're trying to determine you have averaging of let's say 1,000 of such vectors, whether this vector is included in the averaging or not. So I think we use some either cosine similarity or something else to get the signal. Yeah. So there may be a better way to do it.
So, but in this case, your server is the
server is the adversary. Yeah.
Server is but what if one of the clients is
one of the clients versus the attack is harder, because now the client is seeing averaging from a bigger group. So I don't remember exactly in that setting whether this is better than the final black box attack.
Okay, thank you.
Yeah, if no question, let's thank the speaker.